Okay, here we are once again at the physics video lecture. It is Physics 4B video lecture 22. So I had a bunch of questions about some homework problems. Let's see where we're going to get started. We're in chapter 27, but these are problems from chapter 26. I think I'll tackle them first. And before, so there was a question about quiz number 9. And so I'll just number these things. This was quiz 9. We had some capacitors and we just wanted the equivalent capacitance. So here we go. Right, if we were to hook this up to a battery between points A and B, things would charge up. And we had C1, C2, and C3. So if you take this as its own capacitor, then we actually have something in series. Okay. So then we have to say 1 over C equivalent is 1 over C sub 1 plus 1 divided by C sub what? We're just going to name it 2, 3, because of course these two are actually a combination. C sub 2, 3. Now, these two capacitors are in parallel. So we can say this equation holds where C sub 2, 3 is the sum of these two. So we would plug that in right there. In fact, we can do the following. We can say we have C sub 2, 3 plus C sub 1 divided by C sub 1 times C sub 2, 3, and then we would invert that result. So coming down to here, the equivalent capacitance would be C sub 1 times C sub 2, 3, which we have right here, C sub 2 plus C sub 3 divided by C sub 1 plus C sub 2, 3, which is just the sum of all three. So C sub 1 plus C sub 2 plus C sub 3. So that was that problem. Other problems were from chapter 26. Yeah. So what we're going to look at is chapter 26, problem 19. Now, problem 19 was really just the direct application of the vector product. So we have F equals Q V cross B. Now, they told us it was an electron, so we have to be careful to have that minus sign there. So I'm saying minus E. And then we can, for the V cross B, we can do the formal IJK, Vx, Vy. This was a 0, Vx, Vy, Vz. And carefully multiply it out and then multiply by minus the electron charge. So that would be your answer. A couple of other good problems going on here. Problem 28. I should actually consult the book here. Well, it was a circular motion problem for a charged particle in a B field where the velocity is perpendicular to the B field. And under those circumstances, we have mv squared over r, so mass times centripetal acceleration, that's the force, is equal to qvb. And if we want to solve for r, we just strike one of the velocities here, and then we have r is equal to mv divided by q times b. I think those were the, yeah. Yes, so what is V? So actually I've gotten a little bit ahead of myself. So V was given in terms of an energy. So we actually have 1/2 mv squared is equal to that kinetic energy. Okay. And so we can solve for V would be 2 times the given kinetic energy, capital K, over m square root. So, okay, so now we have V, we have that, we have these other quantities, so we can get the radius. Okay, so if I were to number these, am I numbering them? Yeah, I could say we have this, and then we have this here, and finally, you know, we have V times t, so the speed times the period is equal to the circumference. And from that we can solve for the period, because now we have V and we have R. Okay. So solve for P, and of course if you have for T, and if you have the period, you can find the frequency as the inverse. Okay. Good, so that would be problem 28. What else is on our list? Yes, so problem 30 was just formal, but not bad either. Really dealing with the same problem up here. So these are the charges moving in the magnetic field where the velocity is perpendicular to the magnetic field, and we get this formula again. So I'll go ahead and start with this again. So in fact, let's say we have mass times acceleration is equal to force, mass times centripetal acceleration, then we have mv squared over r qvb. Of course, we can cancel a v on both sides, and then we actually have m times v is q times b. And as I recall, the book had the uppercase r there, so we'll do that. So we got one of the b's, we have q times b times r. And they just told us to identify that as the linear momentum p. Okay, so we have that part of the problem. The other thing we can do, so I'll just call this 1. The other thing we can do here is solve for V again. Okay, so V is going to be equal to QB R divided by M. Right? Now the kinetic energy is going to be 1/2 mv squared. Okay, so that's kinetic energy, capital K. And so we just write 1/2 times m, and then we square this expression, so we have q squared b squared r squared divided by m squared, and then that final answer will now be the kinetic energy is equal to q, b, and r all squared divided by 2m. And I think that's what we had there, yeah. So that was just symbolic manipulation. These are useful when you inject a particle into a field and generate that circular motion. You're typically injecting it with a certain kinetic energy. The reason being, I'll just add this, is because you're doing this, Q times V. You know, you're doing your work kinetic energy theorem. So work equals kinetic energy, or I'll just put it in the arrow, you know, work convert to kinetic energy. So you send your charge across a certain voltage. You can imagine you dial in the voltage you want, send your charge across that. Then it has that kinetic energy, and there's a relation that holds. The Q over M, the E over M experiment makes use of relations like this. Okay, that would have been problem 30. Problem 32, this one was a tricky construction. Same theme as this. So I'm just going to set it up and show you what I got. I actually got the whole construction right here. So we're looking at problem 32 now, chapter 26. And we had this picture, so this is chapter 26, problem 32. We had a region with a B field and whatever, into the board. I didn't even draw it right here, but yeah, we had a B field over here and no B field on the left side. And so we enter with a speed V and at an angle theta. So, and theta is with respect to here. So let me, okay, with speed V, and here's our angle theta. I got that right? Yeah. Okay, here's the thing that happens. I'll do it in blue. As soon as we enter this field, we're subject to the magnetic force, and we're going to have part of a circle. Okay. On the other hand, as soon as we leave the field, we're coming out at an angle again, which we named phi. And phi was this angle here. And we had a distance d right here. Okay, so that was an interesting problem. Now, here's the thing, the physics of this is, first of all, that the magnetic force does no work on the particle. So because F is equal to Q V cross B, the force is always perpendicular to the velocity, and that means there's no work done. No work is done on the charge. So its speed stays the same. So if it enters the field with V, it leaves with V. And then this is just a chord across that circular arc, and you're going to be able to conclude that this angle phi is equal to theta. So I could even say that's by the symmetry that we have in our problem. Phi is equal to theta, whatever that was. So once we have that, and this being a part here, let's use another color. This here being part of a circle, right, of radius r, you can do a little bit of geometry. I labeled a bunch of these angles and worked my way through, and I found that D, so part 3 here, I found that D is equal to 2r cosine of theta. So see if you can tease that out, okay? Just after you've concluded these angles are the same, you just work your way through. D is equal to 2r cos theta. Yeah, so I labeled a bunch of different angles. Leave this out here. 2r cos theta, and then that actually does the trick. Everything else follows. Then you can use, I'll just write here use our expression from up there. V is equal to QBR over M. R is equal to MV over QB, etc. R equals MV over QB, etc. And it comes out. So yeah, it was an interesting problem. A little bit of construction here. I've left out the details of this construction, but they're pretty straightforward. Label all your angles that you have to and work through a couple of relations, and you end up with D is 2r cos theta. Okay, good. So there's our homework review. And next I'll set up what we're doing in chapter 27. This is some really interesting material. Sources of the magnetic field, namely currents being the source of the magnetic field. Let's go ahead and make some space up here. Okay, we had done a bit on these sources of the magnetic field. Let's see what we have going on here. Yeah, this can be nicely summarized. So, sources of the B field. Electric currents. There's material in the chapter on permanent magnets and other things like that that we're not even going to get to. We're primarily interested in the electric currents this time around. And we had the Biot-Savart law, I'll write that down, that infinitesimal field element increment mu naught over 4 pi, that's just the magnetic constant we've looked at, times the current times ds cross r hat, which is a unit vector over r squared. So it's a 1 over r squared behavior, and this ds, of course, is, you know, some infinitesimal length element along your current, and this r hat is actually the unit vector that points at this point r in space. So when you integrate this up, you have your work cut out for you when you actually want to do these integrals. U naught I over 4 pi, we're just going to write it with an integration. And it is a, you know, it's a line integral along a curve. ds cross r, hat over r squared. But the straight wire case, I really just gave the answer. I have actually a longer calculation of it, so does your book as well. But the straight wire answer was our next point. So let's work right on here. So this long straight wire is really the crucial expression that we wrap it up in coils and stuff and generalize. Okay, so the next point, we have a long straight wire, I'll call it. Understood that we're talking about a current in the wire. And if the current is in this direction, then we have circular B fields going around here. And if the radius there, the distance, perpendicular distance from the wire is going to be A, then we have B is equal to mu naught I 2 times pi times A. Perpendicular distance. And what about the direction? The direction is given by that right-hand rule. Okay. So direction by the right-hand rule. We'll do more of that. Okay, so, and then I did the field of a straight wire. Then I did the field of a current loop. I'm not going to do that right now, but it's in the notes from last time. We did the Helmholtz coils. Someone may want us to discuss those later on. Next week, we'll see. Good, but we want to generalize this situation right here. So now what we're going to do is consider this field. So next, consider this example. Mainly this example right here, we're going to do an integration. Integrate. Basically integrate along, I'll just draw another one. Integrate along one of these curves here. I think I'm going to change the letter to R. Actually, I don't have to change anything. Integrate around the circle. And what we're getting then is the line integral of the field dotted into this length element again. So what I'm showing is we're just doing an integration. I chose this blue one. Just integrating around. And of course, in this very simple case, our B and our ds are parallel to each other, so that's just going to be a trivial integral. But before we get there, we know that for this example, the B field is mu naught I over 2 pi, going to be A or R. We'll call, we're doing the outside one here, it's R, okay? So mu naught I over 2 pi R, and the integral let's do like this, and dot it into that ds, which is parallel, so we have r d theta. That's our ds. R d theta is going to go from 0 to pi. And when the dust settles, what do we have? We have mu naught I over 2 pi. We have r over r cancels. Then integral d theta, 0 to 2 pi, just around the circle, gives us a 2 pi. That cancels, so we have mu naught I. Okay, so it looks like almost the same thing we had before, just, making use of this expression. But this generalizes to the following law. So the line integral of the B field around a closed curve, that's what that circle there means, around a closed curve is equal to mu naught times the current that is enclosed by that curve. The current that goes through, right here we had a surface, that blue circle, and the current going right up through it. So let's put that in words. So here, I'll go ahead and, this is Ampere's law, and I'll put in words what we have there. The line integral of the B field along a closed curve is equal to mu naught times the current passing through that surface, through the surface bounded by the curve. So line integral equals mu naught times current passing through the surface. Notice the line integral bounds a surface. In this case, we can think of the line integral just bounding a flat disk. Okay. Current that passes through the surface. That's a little short, okay? Because that's a line integral around a surface, and that's the current passing through the surface. So I had to do another picture here. I've got that, and I've got this surface that's being pierced. Think of it that way. It's a disk that's being pierced here. Can I get some perspective on that? Right, imagine that. Coming through the bottom, piercing that surface, and the line integral is around that surface there, and the current is going through the surface. So this would generalize. Suppose I had a more complicated situation, maybe a half a dozen wires coming through here every which way. Much more complicated, but this law would still hold, right? The line integral around the outside, and it would be all of the currents piercing that surface. Okay, good. Important, we're eventually going to get a list of all the basic laws in this integral form. So Ampere's is next. Remember we had Gauss's law some time ago. That was an integral statement as well. So that's where we're headed. So yeah, let's try this a little more. So Ampere's law, once again, the line integral around a closed curve and this line integral, we'll call it star this thing here, b dot ds. This is equal to mu naught times what? The current that passes through the surface bounded by the curve. Let's write that down. Mu naught times current that passes through the surface that's bounded by the curve. By the curve that we just talked about. Okay, I'm going to consult the clock here. How are we doing for time? Okay, we've got nothing but time. So next we're going to do a slightly more advanced example here. So the example I'm going to do is going to remind us of the Gauss's law work we did with the electric field some time ago. So what we're going to have is a straight wire of radius r. Uppercase R. So it's that scenario up there, except we've got this long straight wire of radius r with uniform current going through it. Okay. With uniform current. Okay. So first of all, if we're outside this wire with a radius r, so if r is greater than capital R, and that's our distance, to some point P, if it's greater than R, then nothing has changed. Then we have this statement here, mu naught, so integral B ds is simply going to be B times 2 pi R. I'm going to erase this stuff here. Equals mu naught I, right side, because that's what's passing through such a surface. And we're back where we started. B is equal to mu naught I over 2 pi R. Nothing different there. If we're inside, so the second case here, R is less than capital R, then this will be a top view. We're looking down on our wire. I've drawn it larger here, and we're out here at this R right here, okay, and the current passing through this thing we get I inside is going to be equal to the total current times R divided by capital R squared, because the area scales as the square of the radius. So when we get out from lowercase r to uppercase r, excuse me, then it's just a 1, right? I times 1. But in the meantime, we have that. And this integral here now, we have integral b dot ds is on the one hand going to be b times 2 pi r. And I should say something before I go on with that. It's the very similar symmetry arguments that we had with Gauss's law. Namely, there's no other directionality possible besides this tangential directionality, whether you're inside or outside. You know, if you're inside and the current's coming out, then your B field has to have this circular nature, because anything else would violate the symmetry. If we had a different component and we just give this thing a twist, it would no longer be the same. And yet if we just give this thing a turn, nothing has changed. So symmetry arguments, again, they're pretty powerful. So good, B times 2 pi r. Now on the right side, it's going to be mu naught times this, I r squared over capital R squared, I r squared over capital R squared. And you notice we get something different now, right? We cancel one of those r's on either side, and what do we get? B is equal to mu naught I. We're going to have 1 power of r, we're going to have 2 pi, and we're still going to have that r squared. So here's the thing, let's go ahead and put this in a box. And these are the two solutions. And if you were to graph them, you'd see they actually match up. When lowercase r is equal to uppercase r, then these two are equal. Because then 2 pi r, here it's that, and we cancel the one on top, one on the bottom. So they equal. If we were to graph this, I'm just going to use this picture. Oh, I'll go ahead and erase. Let's do a graph. Of these two functions. So this wire of finite radius with a uniform current inside is going to look like this, its graph. It's going to grow linearly, that's this bottom one here, out to capital R, and then the top one is going to match that value and decrease as 1 over R. We had something related to this with Gauss's law. And on tonight's homework, I'm going to assign a problem like this that takes it one step further, but it's not hard, okay? Or actually a couple along these lines. So if you study this one, you'll be able to do the homework without any problem. Okay. So next in line, I have some more Gauss's law. Actually, consult the clock again. Okay, perfect, we've got time. Okay, what I want to do now, in preparation for what's still to come in the following chapters, is set up the laws of electricity and magnetism that we have so far. Laws of electricity and magnetism. So before we introduce something new, let's just get these formulations going, because we now have some, another integral law that we've just been talking about. So the first one is Gauss's law for the electric field. We have the integral of E dot d area. I'll write it this way. So the electric flux is equal to the enclosed charge over epsilon naught. And we did a little bit of work with this. This is also equivalent to Coulomb's law. So this one contains Coulomb's law, so it's very important. But it's it's this compact formulation just in terms of the integral. Now the second one, I'm just going to write down and then describe it a bit, because so this is Gauss's law. And for the E field, there's also a Gauss's law for the magnetic field. So let me just write that down. The closed flux integral for the B field, so this meant, for a closed surface, that's a surface integral. You can write that. Closed surface. Same here, closed surface. Yeah, for the B field, it's equal to 0. Now, where did that come from? It came from the fact that we can never isolate a magnetic monopole. We can never isolate a north or south pole. They always come together. So let's write that down. Actually, let's first of all write down Gauss for the magnetic field. This is Gauss for the electric field. And I'll write here, because we cannot isolate a magnetic pole. We always get a north and a south. Magnetic pole. And the way we learned that in this chapter is that we saw that even a single infinitesimally thin current loop has a north and a south pole. Infinitesimally thin current loop, it actually produces a dipole field, and you can't get any thinner than infinitesimally thin, okay? So a little current loop does that, and if you were to draw a surface, let's do a red surface, if you were to draw a red surface around here, in terms of your integration, what you would find is that every field line that leaves keeps going and then it enters again. You get these closed field lines, and so you get the negative contribution. So as it's leaving, you get one contribution, say positive, and as it enters, you get a negative contribution. So that sums up to 0. So the magnetic flux through a closed surface vanishes. Our third law is now Ampere's law. So we have 1 and 2. I'll go ahead and write the third one here. So the third law is, as we just saw, closed curve line integral is equal to U naught I. And actually the right side of this can be turned into a surface integral, because just as in this picture, the current is piercing the surface, which is the surface bounded by the red curve. Okay. So that's where we are so far. There's going to be an addition to this law, and then there's going to be a fourth one, and we're actually going to have all of electromagnetism in these 4 laws. Plus a few, plus some spare change. So that's the plan. The next thing I'm going to do is an analysis of Ampere's law. Because there are situations here where we're going to see there's something missing. And I was checking our text brings that material later on, but we're going to do it in the context of everything we know so far. Okay. So, analysis of Ampere's law. And that analysis goes like this. I need a good picture. So, let's imagine we have a parallel plate capacitor. So these are circular plates. That was my, yeah, okay. That's my attempt at some perspective. Let's try it again. So I have these circular plates. I'm giving them a little finite thickness to indicate some perspective. Okay. I think I had a better way of, yes I did, I had a better drawing. Once more with feeling. Let's try this. Here's how I did my perspective. I did it over on the right side. Yeah. Parallel plate. Another parallel plate. Okay, art is art. Okay, there we go. So these are parallel plates. So think of a parallel plate capacitor, and imagine we have a current flowing this way. Good. Okay, so we have a current flowing this way, and they're charging. So what's going to happen is we're eventually going to have plus Q on here on minus Q on there. But we started with no charge. We hook them up, and we learned that these things charge over a finite amount of time. And in the process of charging, you're going to get some E field across them. Okay. So here's the thing. If we do Ampere's law right here, there is exactly this. But if we do Ampere's law across this gap, so far there's nothing because there's no current, there's an E field. But there's a way to equate the current flowing on this side with the E field building across the gap, and that's what we're going to do. That will be called the displacement current. So I'm going to write as the capacitor is charging, we have, first of all, current. I'll just write current, current here, and by here I mean right there and right there. But at the same time, we have E field building up inside. So what we're going to do is equate this current here with the E field that's building up between the plates, because we're required to do that by the continuity equation. A couple of different ways to justify it, but this is the way we're going to talk about that. As the capacitor is charging, we have a current on the outside, and two, we have an E field between the plates. Okay. So let's analyze that. We'll be able to make use of the Gauss's law up there. So this is a formal thing, but we'll see. It's really principled. So what we have is current here, E field between the plates, and a charge building up on the plates. I'll put that as part 3. Charge is building up on the plates. So what we're going to have here is, just as with Gauss's law, we're going to have an electric flux through this surface here, through the red surface. We're going to have an electric flux. So let's write the following. Let me put this down. So now, from Gauss's law, the original one, we have phi sub E is equal to Q enclosed over epsilon naught. Okay. So the flux through the surface here, the red one, is phi sub E. And the Q enclosed over epsilon naught is the Q that is built up on that plate. Okay. So now what we're going to do is multiply over, so just epsilon naught times phi sub E is equal to Q closed. And then we're going to take a time derivative of both sides. Let me bring that over to here. So we have epsilon naught electric flux equals Q. Let's write Q enclosed. If we take a time derivative, we have epsilon naught d flux dt is equal to dq dt. But what is this? dq dt is a current, charge per time. I sub d, this is referred to as the displacement current. This was introduced by Maxwell, displacement. Right, it could be it could be across a vacuum, right? But its definition is given on the left side of the equation, and this is added to Ampere's law. So add I sub d to Ampere's law. Ampere's law, let's write that better. And what do we get? We get 3, I could call it 3 prime, integral b dot ds is equal to mu naught I plus I sub d, and that's equal to mu naught I plus mu naught epsilon naught d phi dt. Okay. Yeah, I want to put that one more time with a comment. What's a good place to put it? Well, no, I'll just go ahead and you guys give this some room, okay? It's an important equation. I'll put a box around it. So the commentary is this. The commentary is that changing electric fields, remember this represents an electric field, changing electric fields also produce magnetic fields. Remember we saw currents produce magnetic fields, but also changing electric fields. Okay? So the situation becomes very rich now. So the commentary here would be that changing electric fields can also produce magnetic fields. I'll put that as a note. changing E also, and that's what a time derivative is, right? Changing also produces B. That's what we'll leave it at for now. I think that's as far as we're going to go. Good. And what I'll do is put down a couple of homework problems for you guys. Where did I have those written down? Yeah, so this would be the homework 22. We're in chapter 27. I'll just put it right here. So, homework 22, chapter 27, and the problems are, these are primarily those Ampere's law problems. I had 3 of them. 49, 82, and 93. 49, 82, 93. Okay, good. So these themes are going to be, the formulations of these integrals are going to continue in the next chapter for a bit. So we got a lot of great stuff to do. Okay, good. See you guys next time.